So most everybody was here yesterday. We talked, so we got started here with the idea of the integral, the definite integral, which is we're defining as the signed area between the function and the x-axis. And by signed area, we mean that if it's above the x-axis, it's positive. If it's below the x-axis, it's negative. Okay? Unless we go backwards with these numbers here, then everything's opposite. So in other words, we normally want A to be littler and B to be bigger, and we read it from A to B. So when we see this S-shaped integral symbol, and we see the A and the B here, we read it the integral from A to B of f of x with respect to x. Go.
Why do we read it bottom to top?
Just because that's smallest. So if you looked at the x-axis, left to right, little to big. You look at the y-axis, right? Think of this vertically like a y-axis, little to big. So it'd be bottom to top. You're right. When you read it in a book, you start at the top and go to the bottom, don't you? But we're doing numerical, right? So little to big would be left to right this way. Little to big would be bottom to top. Okay? And so that's why we read it down. Okay? So it'd be, so that's how those symbols are read. So, now why do we have to worry about it being backwards? Well, it just shows up that way in problems from time to time, and we need to have a meaning for that. What is the meaning for that? And again, it's going to become apparent to you over time as we go through this, what we're going to use this for. Just like derivative. We talked about the derivative as a slope at one point. And then we proceeded to find all these uses for, the derivative, this instantaneous rate of change, chapter 4, optimization, just a variety of things where derivative, L'Hopital's rule, right? Finding limit problems, a derivative was involved. There's all kinds of different things, some mathematical uses, some more real life kind of uses. Same thing is going to be true for this area. And then tomorrow, we're actually going to, be able to make kind of connection between what we've been doing. Okay, so we've got chapter 5 to do, kind of a long chapter. You look at the assignment sheet, a lot of stuff in there. Gateway test we talked about is coming up. With antiderivatives, we'll see how antiderivatives play a role here. We'll actually start that process tomorrow. Okay? Chapter 6 is a short little chapter, doesn't take very long. Chapter 7 then is where we get into some more uses of this area, even though we're getting into some already. Matter of fact, we started with one yesterday. The area under a velocity curve represented what? The distance traveled, right? So there's already a use for area under a curve like this, okay? So if this was a velocity curve right here, this area would represent the distance traveled, okay? All right, so we had a couple of just rules that we will follow with the integral symbol. Now listen, these are very much like the derivative rules we had, okay? Where we can take and we can split apart an integral. Now we didn't make a big deal about the derivative rules. We didn't split apart functions very often. However, we will do that more often with integrals because the integral symbol, you didn't write the derivative symbol other than a prime very often. I mean, you use the prime, but not like we have this integral symbol. Okay, so let me show you an example I'm talking about. Here was the rule we had with, hey, stranger. Here was the derivative rule we had that would be similar, okay, similar to this one, okay? Here's the derivative rule we had that's similar to this top one, all right? And what did it say? It said, well, if you're adding two functions together, we can do the derivative of the first one, and then we can do the derivative of the second one, and we can do their individual derivatives. Now, we can do that with minus signs, too. Now, we wrote that down. That was at the very top of our page of derivative rules, but we never thought about it that much. If I gave you the function x squared plus sine x, what did you do to do the derivative? You just did the derivative of x squared, then you did the derivative of sine, and you just did it. But that's the rule you were doing. Now, why is it important to have a rule, then, if it's not a big deal? Well, it is a big deal. Because can you do that with this? Right, no, you can't. You got to then we had to come up with the product rule. We had to have a special rule for a product. Well, guess what? Same thing's going to be true here. If you've got an integral and you've got a function times another function, you're not going to be able to just split those apart. You're not going to be able to split those apart. Okay? And so, very much like it was with the derivative rules. Okay, so we had a similar kind of rule like that. All right, same thing with this. We said if there's a number setting outside of a function, it just hangs out there while we do the derivative. Well, the same thing's true here. If we got a constant setting outside of a function, we can just pull it out and it can just set out there while we do the integral. Same thing. Okay, so it's very much the same rule that we had there. All right, so we're going to use that in some of our problems. And the last one we had was this rule here, which said the integral from A to B, which would be this area. And so, Tyler, you missed we were just reviewing here. This was our definition from yesterday's video. This thing called a definite integral, okay, is this area under the curve here, okay? So this area from A to B, okay, this area from A to B can be thought of as made up as the area from A to C plus the area from C to B. Now, it seems very obvious. But what we talked about yesterday is they actually don't have to be, the C, this part, doesn't have to be in between the A and the B for this to work. Okay? So, we were talking about how areas below are negative, or if we go backwards, it's negative. Well, here's an example where this comes out. So, let's say I had this. Let's say I had the integral from 2 to 7 for some function. Okay? Well, it's pretty obvious that that would equal the area from 2 to 4 plus the area from 4 to 7. Right? Everybody would be on board with that. That's pretty obvious, right? The area from 2 to 7 is going to be equal to the area from 2 to 4 plus the area from 4 to 7. Obviously. Okay? But look at, now let's pretend that the function was all above the x-axis and everything, right? So everything was positive area. Okay? Now, what if I wrote this? The area from 2 to 7 is equal to the area from 2 to 10 plus the area from 10 to 7. Now again, notice how the 4 is in this place where the C is. Here the 10 is in that same place. According to this rule, this should be a true statement. The area from 2 to 7 is equal to the area from 2 to 10 plus the area from 10 to 7. So let's think about this. So let's say the area was all above the x-axis, right? So we have this piece from 2 to 7. Well, let's just draw it. Okay? So we got, here we go, here's 2, here's 7, here's 10. Okay, we got this area. Okay, so the area from 2 to 7 is right there. Okay, so the area from 2 to 7 would be the area from 2 to 10. Uh-oh, what happened? We got extra area, don't we? Right? That's a bigger than our actual area, 2 to 7. So we got 2 to 10. So we're going to add on 10 to 7. The area from 10 to 7, well, that's this area. But what is this area? Negative. Why? Because we're going backwards. That's what we were saying at the beginning today, right? If you go from 10 to 7, that's going backwards. Well, if you go backwards, everything's opposite. So we go backwards from 10 to 7, this area is negative. So if you take this area, 2 to 10, add on that area, but make it negative, what do you end up with? 2 to 7. So it still works. So the bottom line is, whether this number here is in between the 2 and the 7 or not in between, it still works. Okay? So that's something that's going to show up from time to time where you'll hear me say, hey, split up the integral. Split up this integral. Okay? And it'll be obvious at that time, hopefully, where to split it and what number to use. Okay? But that's just a rule, another rule that comes in handy with integrals. Okay, so let's talk about your homework here. So let's talk about 5 through was it 5 through 14? 5 through 14 was using this picture here. So guaranteed on our next quiz, which is scheduled for about a week from now, about Wednesday, I think, you're going to have to do something like this, okay? Find these areas using geometry, okay? Now, between now and then, we'll have other ways of doing it, but here we would use geometry. Any questions on 5 through, let me just read through the answers. Maybe you didn't take a picture or didn't look at them here. So let's see what you got for the answers. 5, I've got answer of 4, 6 is 9 pi fourths, 7 is 4 plus 9 pi fourths, 8 negative 4 pi, 9 is 0, 10 is, they've got a decimal here, negative 13.5 roughly, so I don't know if you left it in terms of pi or not, but you can check yours, negative 13.5 they have roughly. 11 is roughly 35.6, 12 is 12, 13 is negative 3, 14 is negative 9. Okay, any of those that you want to talk about? Got to remember that the area of a circle is pi r squared. These are quarter circles here, so that's how come this was 9 pi fourths. The radius is 3, so 3 squared is 9 pi, but it's a fourth of a circle, so it's 9 pi fourths. Which one? Number 9. So number 9 says the integral. Oh, yeah. Yeah, good. Thank you. Something we did, and something that didn't come up yesterday, and funny, the other class didn't ask about it, but so maybe they all got it. I doubt it. Must have. What do you think? What's the answer? What was the answer then? What did I say the answer was? 0. Why? Yeah, there's no integral, right? I mean, it's kind of like doing a rectangle with 0 width, right? It's kind of that reason. You know what I mean? There's just nothing there. There's no room. So by definition, any time for any function, these two numbers are the same. That area, that integral is automatically 0. Automatically 0 every time. Okay? Good question though, because that's one that you could wonder about, and so you should ask. That's good. What else? Anything else on those? Okay, just basic geometry, right? I mean, you're going to have some trapezoid. Well, not really any. Well, here would be a trapezoid, I guess. Right there would be a trapezoid, right? You can almost just count squares. It's pretty easy. There has, but normally we're going to think of this as a trapezoid. We're going to think of that as 1 and 3. So the area of a trapezoid is your two bases. We're going to do a lot of trapezoids, so you better be comfortable with the trapezoid formula. These are the bases, okay? Because it's a trapezoid tipped up on its end. And then this would be considered the height of the trapezoid right here, which would be 2, okay? And so that area would be 4. So trapezoids, part circles, of course you got a triangle here, half base times height, that kind of stuff. Okay, all right, let's move on then to 15 through 22. Looked like there were a lot of questions on that. Now, Allie and I was commenting, I said this, actually there was more of you, I think, had pictures than first period we did, and I asked him, I said, well, how do you do 17 without a picture? I don't know, that would be hard for me to do without a picture. Now, unless you misunderstood the directions and you just typed it into your calculator, right? We did a couple of these yesterday where we drew the picture, it made a geometric shape, and that's how we did the areas. If you read the directions, it says evaluate the definite integral using a graph of the integrand over the interval of integration. Using a graph. Now, of the integrand, what's that mean? That's this right here. That's just the integral. Okay, graph of the function. So they wanted you to draw a graph. So on the quiz, if I say sketch a graph to find this integral, now by then we're going to have some other ways to find these integrals too. Okay, and we'll talk about the difference between them. But I want you to sketch a graph. So, what do you want to see? Some of you had these blank. Some of you had, questions for sure. What do you got? 18. Okay, so 18 says the integral from -2 to 1 of w dw. Now, why is there a letter there? Okay, that's a comment I heard from a few of you. I didn't know what to do with these letters. Why is there a w there? Does it matter? What could it be? Could be an X. We would usually use an X. But what they're trying to do in this section here is they're trying to show you it doesn't matter. It's like German shorthand, right? We've used T for our input variable. We've used, right? And early this year I talked about parabolas, okay? Y equals X squared is a parabola. Y equals U squared is a parabola. Y equals W squared is a parabola. Y equals Z squared is a parabola, right? They're all parabolas. It doesn't matter what letter you use. So what graph is this? All lines are straight. Diagonal line, 45 degree, right? Y equals X is what we're talking about. Now, yeah, it's Y equals W. I don't care in these integrals If you want to take out the W, when you write it down, if you want to write that as x dx, go for it. That's fine. I don't care. Doesn't matter. You know, now later on, we're gonna have a situation where that variable is gonna kind of matter and so forth, and right. But don't worry about that till we get to that point. Okay. So with respect to W, so that's just like having x dx in there. So this is the function y equals x. That's what it is. Sometimes the simplest ones are the most confusing. Okay. So there's a line y equals x, and we're supposed to do the integral from -2 to 1, which means we want the area. Well, let's put my grid on here. Well, you guys don't have a grid, so. -2 to 1. It doesn't matter if it's drawn to scale. That's going to make 2 triangles, right? That's the area. Remember, we always do the area between the curve and the x-axis. It's always between the curve and the x-axis, okay? So we always draw our areas like so. So it's just 2 triangles. Okay, so what is this y value right here? We'll plug it into our function. Oh, it's y equals x, so it's the same. So that's going to be 1. This can be -2, right? So we got a triangle that's a 2 by 2. What's the area of a 2 by 2? 2. 2 times 2 times a half, right? So that's going to be 2. Now, is that going to be positive or negative area? That's negative area. So we got -2. Plus, what about this one? 1 by 1. That's 1/2, right? 1/2 base times height. So that's 1/2. What's -2 plus 1/2? -3/2. -3/2. -1/2. -1.5. Makes sense because it looks like there's more negative area than there is positive area. Okay? Yes. 23. Okay, now that gets into a different situation. So let's see if there's any more questions before for 22. 15 to 22. Anybody else? 21. Okay, so 21 says the integral from -2 to 2 square root 4 minus s squared. Okay, now, so let's compare that to what we were doing back here. Lines and part circles, right? I mean, if you think about it, the only geometry areas we know how to do are shapes with straight lines. There I said it. Straight lines and circles. And the only curve we really have an area for is circle. Now, there is an area formula for ellipse. I don't know if you learned that last year in advanced math. I don't know if you talked about it. There's an area formula for ellipse. But other than that, there's really no area for a curve other than a circle. Otherwise, it's straight lines, trapezoids, triangles, those kind of things. Squares, rectangles, and the like. Okay, so that means these graphs are going to have to be one of those. Well, we need to get to the point in this section. I mean, for next Wednesday's quiz, you need to recognize that that's a half circle. Okay, I mean, here's the equation of a circle. We did it on day 1 or 2. I think our very first homework assignment, we talked about area of a circle, or excuse me, equation of a circle. That's it right there at the origin. If you solve that for y, you get this. If you square root it, you get plus minus square root of r squared minus x squared. So some number here, which would be a radius squared minus an x squared, you see that inside of a square root. Every time, that's a circle. Okay? Now the plus minus is a top and bottom half. So if this had a negative on it, we'd be doing the bottom half. If it had a positive, we'd be doing the top half, which it's positive. So that's going to be, because of the 4, that's going to be radius 2. So it's going to be radius 2, centered at the origin, like so. It's going to go up, right? It's going to be a half circle. So we're just talking about that area. Well, that's just pi r squared. So pi times 2 squared, 4 pi, but it's only half a circle, so we get divided by 2. So that's going to be 2 pi. Okay? And we just do that with simple geometry, right? But first we got to recognize that makes a half circle. Okay? So drawing the picture. So yes, I did show you. That was my mistake. I never should have showed you how to use a calculator yesterday, right? You can just type these into your calculator, right, and get that answer out. And later on, when we get into chapter 7 and we get into story problems and uses of the integral, then yeah, the hard part of the problem will be setting up the integral. Once we get the integral set up, we'll just go to our calculator and type it in. Yeah. So there will come a time where we will absolutely do that. but not right now. Okay, not right now. All right. Okay, so now 23. And let me back up a minute. I meant to show this. I meant to show here at the beginning, and this would be good for Tyler to see. So when we were talking about positive and negative areas, right? So the area from A to B, this is going to be a negative area. Just a rectangle, it's a 3x2, so it's a -6. But if we go backwards, if we go from B to A, and you look up here, -2 to -5, that's backwards. -2 to -5, notice it's got a positive answer. Okay, same thing over here. If we go from D to E, that's the integral going from 7 to 9. So that's the normal direction, left to right, 7 to 9, that's going to be a positive area. It's a trapezoid. Okay, but if we go backwards, E to D, if we go 9 to 7, that's going to be a negative area. It's above the x-axis. Normally that'd be positive. Now it's going to be negative. Okay? All right. So, again, this one, -2 to 2, that's going left to right. That's going to be a positive area. All right, 23 you said. 23 says the integral from pi to 0 of r squared dr, and they had told us in the directions that the integral from 0 to pi of u squared du was pi cubed over 3. So that's what they had told us in the directions. Now, they had to tell us that, because what area is this talking about? The area under what? Parabola. Remember we did that yesterday, and I had the wrong number. Trying the calculator didn't come out right. Okay, because I was just making up a number. Well, this is actually true. This is actually, if you type this in your calculator, that's actually what you would get. So what they're saying is, if you took a parabola and you wanted to find this area, see, so that's the problem we have. This is a lot like the slope problem we had. We wanted to do slope at one point. Can't do slope with 1 point. How do we do it? We knew how to do slope at 2 points. How do we do slope at 1 point? Well, we let the 2 points get really close together, and we came with the derivative formula, and then everything went from there. Well, that's kind of where we're at with this. We would like to do this area. We know that if this was a velocity curve, that area would give us the distance traveled. We'd like to find that area. Unfortunately, there's no geometry that will do that. That's not a geometry shape. How do we know this? Well, the calculator knows it. They told us that. How do they get it? That's what we're going to be figuring out. Okay, how do we come up with that? Okay, it's like trying to find slope at 1 point. How do we get that? Okay, well now what is this? How's r squared dr compared to u squared du? It's the same thing. Well, no, I'm not talking about that. I'm talking about the r squared dr. It's the same thing. It's just a parabola, right? It's just a parabola. Except this is going backwards. So what's the answer? Negative pi cubed over 3. It's just going backwards. Right? This is positive, so if you go from pi to 0, it's just negative. Okay, what's another one in that section? 25. Okay, so let's look at that. Well, here's where we're going to use those formulas. Okay, now we're going to do this. Now, I think, what did I say the answer, or I didn't say the answer. What did the back, let me look it up. What was the answer in the back?
Pi cubed minus 3 parentheses pi cubed.
Okay, and then that equaled, you didn't write down what it equaled. It equals 0. The back didn't say 0. I'm thinking maybe it did, but it doesn't matter. Okay, so the answer is actually 0. Isn't that interesting? And the area is 0. Well, let's look here. So number 25 says the area from 0 to pi of pi squared minus 3t squared. They put parentheses around that. I don't usually. You can't. Doesn't matter. They don't need to be there. This, by the way, is, we saw that in those directions. That's called the integrand, the thing that's inside the integral, the function here. Remember the dt, we said that's just with respect to, is all that is. But what we're trying to find is the area under this graph. Now, one thing we could do, I did this for the other class, so I'll show you. Oh, there's our pictures again. All right, if you look at, I went ahead and graphed this. I went ahead and graphed pi squared minus 3x squared from 0 to pi. There's pi over there, 3.14 at the far end. Now, this area, the answer to this should be this area right here. So it's this plus that. Does it look reasonable that that is 0? Looks reasonable, right? It looks like this positive probably is very close to the same as that negative. They would cancel each other out. And the answer, according to the answer book, is 0. But that's what we're finding, right? That's what we're finding in this problem is that area, okay? But we're not going to, we don't know that. It looked like it was maybe close to canceling out, but we don't know that. We don't know how to find out for sure. It's one of the things we're going to be working on. But for right now, since they told us this, we can use the rules that we've learned, which are these right here, okay? So all we do, and we did one like this yesterday, we did a couple of them actually, is we just split this apart. So we start here by splitting this apart. So this would be pi squared dt, and then minus, and then this would be 3t squared dt. So I just split that apart first. Okay, then what was the other rule? What did the rule say about this 3 here? Bring it outside. So let's put that 3 out here. Now, what is that right there? That's this right here. That's the same as that right there. It's just using a t instead of a u. It's the same thing. So this, in the red, is pi cubed over 3. So this is why the back of the book said, had a 3. This is what you read to me, I think. Cody, was this, right? They had 3 times pi cubed divided by 3, because they're just substituting pi cubed divided by 3 here, and then they got a 3. And then the question is, how do we get this? Well, what's pi squared? That's kind of a loaded question. I'm asking you to read my mind. What's pi squared? I obviously don't expect you to know the value of pi squared. What is it? If you're going to graph it, what's it look like? No, I'm just tricking you. No, what's pi squared? It's a number. That's what I was looking for. Pi is just 3.14. Pi, that's not a parabola. Parabola is when you do x squared or t squared or a letter squared or variable squared, right? Pi is a number. Pi squared is a number, 9 point something. So what's a number look like when you graph it? Horizontal, right? You can't say straight line for that one. Earlier you were telling me straight line for that, right? See, you can't use it. You can't call both of them. Well, they are both straight lines. You're right. They are both straight lines, but then every line straight. It's a horizontal line, okay? So here's what it is. Here's what this area is. It's pi squared. I don't know what it is, 9 something, right? But that's pi squared up there. And we want to do the area from 0 to pi. What shape is that? Roll, right? It's a rectangle. And it's pi wide, and it's pi squared tall. Base times height. So it's pi times pi squared is pi cubed. So this answer here is pi cubed. You can't get that without drawing a picture unless you're getting the hang of it and can visualize it, but I don't think many of us are at that point right now, right? So that's why I was looking at that as I was coming around and thinking, how do you get a problem like this without, a picture, right? Well, you look in the back of the book, probably. You're not sure what to do. This is what we got to do. We got to draw a picture, right? That's what we're talking about. We're talking about area. That right now, all we know about this integral symbol is it means area under this curve. How do you find that area without drawing a picture of the curve, right? I mean, you can't. For the most part, right? I mean, this one they gave us, right? This one right here, I drew it, but it didn't matter. They gave that to us. But otherwise, we probably got to draw a picture, or at least visualize it. Okay, anyway, right here, the 3's cancel. Pi cubed minus pi cubed, we get 0. So that's how we would use the formulas. We would split that apart, pull that 3 out. But when you have a number only in here, it's just a horizontal line, okay? All right, so what about, let's go down to 33 through 36. Any questions on those? 36, okay. How about before 36? You sure? Because it sure looked like some of you had questions when I went around. All right, 36. So, we got the integral from -2 to 5, h of t plus 1 dt, right? And they tell us that the integral is h of, that's not h of t, it's h of x. Doesn't matter, but we'll get it. And what did they tell us in the directions? Sure nobody has a question on 33, 34, 35? Okay, well you can ask me in the video. Okay? 32, no, we didn't do 32. 33 is 74. 34 is -105. 35 is -18. Okay? All right. Well, I just want to make sure. Cody claims that I confuse everybody just so I can look at your faces and laugh. So I'm giving you plenty of opportunity to ask questions now. So let's make sure. All right. So 36 is this right here. Okay? So I'm not going to make you raise your hand or anything, but the common mistake that people make is they put -10 on this one. Okay? Common mistake is they put -10. Now, what you're supposed to do on 33, 34, and 35, especially 33 and 34, is split them apart, right? Split them apart, pull out the 3, just like we did on that last problem. Okay? So you're told over there in the directions that -2 to 5 of h is -10, right? Or no, -11. Okay? You're told that this is -11. And then it says plus 1. So you go, oh yeah, so that's -10. Now, what is the answer for 36? It's -4. It's -4. Okay? There are two ways we can do this. Now let's leave that there. There are two ways that we can do this. Okay? One way is to do what? So you guys got -4. How'd you get it? So split it apart. You split it apart first, though, right? So it's the integral from -2 to 5 of h plus the integral from -2 to 5 of 1. Right? We split it apart, just like we did before. Now this we were told is -11, right? And this would be a horizontal line at 1, just like the pi squared example we did. And it goes from -2 to 5. So the area from -2 to 5, well, what is that? That's a rectangle that's 7 wide and 1 tall, which is 7. So -11 plus 7 is going to be -4. Now that's probably the simplest way, the way I would recommend that you do it. Okay, now, to understand the concept of it maybe a little better, think of it this way. Think of this being the h graph here. Okay, there's the h graph. Okay, whatever. -2 to 5. And that's got an area. Now the area is supposed to be -11, but I'm going to make it positive just to make this simple for us for right now. Then we'll do it the way it is. Okay, so if I take this area, whatever it is, and I take that h graph and do what? What's the plus 1 do? Moves it up 1. So if I take this piece of graph right here, let's make it red now, and let's shift that up 1. Wouldn't this be the original h right here? Wouldn't that red be the original h? Would everybody agree with that? So here's that black area, whatever it is, let's say it's 20. We shift that graph up 1. There's my original 20. What have I added now? What area have I added? I've added a rectangle on the bottom that's 7 by 1, which is 7. That's why you can't just add 1 to the area. You've added a strip of area. When you shift that graph up, you've added a strip of area down there. Okay? And it also works if it would have been negative. right? If the H graph, oh, come on, do I have a, there we go, ignore all that. So let's say we had a strip of, let's say we had our area down here, it was negative 11. Here's our function, so it's negative 2, what was it, to 5? So that's negative 11. Now let's say we shift that up 1. So now my graph's there. Wouldn't this be the original negative 11 right there? Right? Right? That would be this original red piece all shifted up, but now we don't have this area anymore. We lost it, didn't we? Now we're only looking at this area. Well, what happened? We lost that. Well, that's now positive. How much is that strip right here? 7. Well, what happened? We had negative 11, but we lost 7, so now what do we got? We got negative 4. We got negative 4, and that's what we had in this problem, right? So it's easy to see if you think of a positive area, you shift it up 1, you got a new strip of area underneath that you just gained. It's going to be the width by whatever you shifted it up, okay? All right, so be careful on one like that. All right, so back to, well, that's it, pretty much it for the homework, isn't it? So let's move on to our one new formula we have today, and that's about it. Then we're going to have work time, and your work time is going to be a lot more of the same. I've got this packet, and on my sign sheet said LH packet, so now you're going to know when you get to the ones on here, you're going to draw graphs. You're going to draw graphs for them, okay, and look at the area. All right, here's the new formula we have today. Last thing in this section, this is still in section 1, average value of a function f of x from x equals a to x equals b, okay? That's what we're talking about here. Average value of a function from x equals a to x equals b. Now, while you're writing that, just talk just a second here. We've said this year that when we use the word average in this class, it means what? Slope between 2 points. Now, several times when I've said that, I've said at least so far, right? It means slope between 2 points. Average rate of change, average velocity, those kind of things, slope between 2 points, okay? Now, we're going to use the word average here also, but it's going to say average value, and so that'll be the difference, and you'll almost always have the words average value together, okay? Almost always. Now, sometimes they'll say mean value, okay? And, well, wait a minute, we already have the mean value theorem. Well, actually, some people call this the mean value theorem for integrals. The one we did was the mean value theorem for derivatives, because it was about average rate of change. This one's about area, average value. So you'll see here in a minute. But we're going to memorize this formula when we hear average value of a function. All right, so think about this. If you had a function from point A to point B, you got a bunch of y values. Doesn't it make sense that there's some number that's the average of all those y values? The problem is, how many y values are there from A to B? There's an infinite. Let's assume it's a nice continuous function. So we can't add them up and divide by how many there are to get the average. Okay? So let's look at this picture right here. Okay, so we've got a function here. We've got a function here from point A to B. Doesn't it make sense, if you just look at these y values, that somewhere in there, there's a y value that's the average of all those y values, right? Makes sense. That there's got to be one somewhere. Matter of fact, let's guess where we think it is. Right here? You think that's the average of these y values? Okay, so go where?
That's good. No.
What do you guys say?
That's got a guess. Give it a guess. 1.68.
Go up a little more, down a little more. We want the average of these y values. So we're kind of looking to see, we got so many above, so many below, right? Is that, what do you think? Go up a little bit, down a little bit.
I think just that good.
Leave it right there. Yeah. something. All right, so let's go with that. So that's the but it makes sense that somewhere there's an average. Now, you can't ignore the fact that while I was doing that, while I was sliding that, there's areas in there. They got that blue area shaded. Now they've got this purple area. And so as we were thinking about that, you're kind of looking at the Y values. You think, well, you got some Y values that are up here above. You got some Y values that are below. You're kind of looking for the middle, right? I mean, that's what you're kind of looking for is the average. But now let's look at the areas that they set. Okay, so if I've got this function from here to here, the blue area would be obviously just the integral. That's the area under the curve. Okay, and as I slid that up and down, the purple is the area of this rectangle here. And just like the Y values, we have some that are above and some that are below. We kind of have areas that kind of seem to be offsetting each other. For example, this area seems to kind of offset that. This area is kind of seeming to offset that, right? Would it be reasonable to assume that if that line really was the average of the Y values, that the purple area and the blue area would be equal as well? Would it be reasonable that this purple area would be the same as the blue area? Right? We got the overlapping parts. You got this part that kind of offsets that. You got this part that kind of offsets that, right? Seems reasonable, okay? Because that's also going to be kind of in the middle. Well, that's what we define the average value of a function to be, is the Y value that causes that rectangle to be equal to the area under the curve. Okay, now there's no way to check that that's the average value because we can't add up an infinite number of values, right? So we just define that to be the average value. Now what would that formula be? Well, the blue area is just this. The blue area is just the integral. So the blue area would just be the integral from A to B. So that would be this. We will in a second. As soon as we finish it. So the blue area would be that. What's the purple area? Well, it'd be our average value. We'll see in a minute how close we were. Our average value, let's just call it AB for right now. So it's this Y value. That'd be the height of this rectangle. And what would we write for the width of the rectangle? What would be the width of the rectangle? B minus A. Right? Just take B, subtract A. All right, now, so to get our average value, all we need to do is divide both sides by B minus A. And we would have, and we'll write it down here in a second, but that should give us the average value. In other words, if the blue area is equal to the purple area, we should be able to find the blue area, divide by the width, and that should give us the height, which is our average value. Now, let's see how good we were. You were off. It says 1.64.
Oh, that's perfect. That's the best guess you've ever had.
Now, the way I remember it is I went like this. You said stop, and I kept going just a little bit. And then you said, okay, isn't that kind of what happened? Okay. All right, we'll give it to you. That's pretty good. All right. So, for our formula, average value of a function. So we'll just call it, we're not going to, I mean, that's it. That's what it is, average value. We're not going to call it anything, whatever, just give it another name, just the average value of a function. Now you got to understand, it's of a function, f of x. So we don't have to do the derivative, antiderivative, anything. We just do the integral of that function from A to B, and we divide by B minus A. And that's just a formula we're going to have to memorize. Whenever we hear, and you're going to have some in the homework, says find the average value. So you're going to do the area, and then you're going to divide by the width. Do the area, divide by the width, and that gives you the average value. So if we go back to that problem we had here earlier, if I wanted to do the average value of this function, if I wanted to know the average of all these y values, we would just do this area, and we would divide by 15. We would find this total area, which you probably found in one of those problems, and then we would divide by 15. Okay? I think it was, did you ever do it? On 10. 10, the answer was negative 13.5. If you take negative 13.5 divided by 15, you get like negative 0.9 or so, negative 0.8. Does it seem reasonable that negative 0.8, negative 0.9 right in here somewhere would be the average value? Seems reasonable. You got more negatives than you have positives. So it seems reasonable that the average value would be down there somewhere. Okay, so it'd be that area, and then divide by 15. That's average value. Okay, that's all we really have to add to it today. Your homework's going to be some more of the same. So on that homework sheet, you're just going to finish that top line, and then where it says LH packet right below that, that's this packet. Now remember, this just came from another textbook. We've had an LH packet before. It comes from the textbook where the authors were Larson and Costello, that's why I call it that. But so this packet, now pay attention, the front page, we're going to skip around a little bit. The front page is 279, but your homework is on 289. So you got to turn to the next page. Okay, it always baffles me how somebody can do that homework on that front page when it doesn't look like anything we have done, even remotely. It makes me think when people do that, they often look at their homework that way. But, okay, so 289 is what it says on your sheet. And so this has some pictures, some geometry areas you're going to find. And then when you get to 11 through 20, that section, that's where you're going to just draw the pictures, just very much like your section today, that 15 through 22, where it had the letters. That means it's a function. You just draw the graph. It'd be a line or a horizontal line or something. Draw a picture, be a triangle or half circle or something like that. And then you just find the area. Okay? So finish the ones in the book, that top line, and then do the LH line.